Assalamu alaikum, everybody. Yeah, so as Salma mentioned, I'm going to talk about some research I did developing like an automated screenline analysis tool. I know that sounds like nonsense to all of you guys, but inshallah we'll explain it a bit further. So yeah, I'll take you guys through like an introduction of me first, and then I'll give a bit of background on the research, the scope, and then we'll talk more about like the technical stuff, the methodology, and then some challenges, and then results and outcomes. So yeah, a bit about me. I'm in my fourth year of my undergrad in planning. So I did this research last year when I was in my 4A. And like I'll explain what planning is a bit. The way I would define it, other people can disagree, is like the process of managing change in our communities, our cities, our towns. And it's really like balancing different priorities, solving what we call wicked problems. So like a lot of different um, parts of planning that you'll hear about is like land use, transportation, environment, heritage, social fabric, and those sorts of things. So for me, I'm specialized in transportation and something called GIS, which is basically it stands for Geographic Information Systems, and it's, to put it really simply, a system to manipulate and analyze spatial databases. And so really the work that I did in this research is related to both transportation and GIS. Um, and then just sort of my experience to give you an idea, I've worked in transit at Grand River Transit. So that was like some of my public sector experience. And then I've done a lot of consulting work. So doing policy planning. So working on like longer term plans, and then also more technical work with like modeling, and then a lot of spatial analysis, which is done in GIS, and what this research is, really about. So yeah, just to give an idea of the research, like what it is. So I was recruited by Dr. Jeff Casello, who is an expert in urban transportation systems. And he was working with the region of Waterloo to do mode share estimates. So to put it really simply, mode share estimates, so like a mode is like any way that you get around. So it could be walking, it could be cycling, it could be transit, it could be driving. And mode share, we want to look at any given time in any given place, what percent of trips are made up by each sort of different mode. So this is an example of a table. So like over here, like 1.4% of trips are made by cycling. Um, and like the most recent data we have for that in the region was from the 2021 census. And the census data has like a number of limitations. First of all, it's self-reported, so it's not necessarily like accurate. Secondly, it just asks for commuting, so it's not concerned with like any other type of travel. It's only like to get to school or work. So really lack of data. And Mocha is important because it helps us inform sort of infrastructure changes, policy changes, and the way that we usually look at Mocha, it's hard to look at like trips in like a whole area. Like region of Waterloo is pretty big. So we'll sort of define like key places where we think it could be more representative of like the overall trend. So that's something called like screen lines and cordons, and I'll explain that further in a couple slides. So like the full project, the full research was looking at like all different modes, 2 week periods, quarterly throughout the year. And the main focus was to hopefully automate that process to make it easier in the future. Um, but specifically, the scope that me and one other undergraduate student had was to work on transit passenger volumes. So in terms of like walking, cycling, driving, it's really easy to, set up these cameras from this company called MyoVision. It'll do counts throughout a certain time at a certain intersection, number of intersections, and then they have their fancy proprietary like technology, and they'll get like all the results. Like, there is like this many hundred cars, this many hundred people crossed, and they can turn that into like uh, the data that they need to calculate the mode share. But for transit, it's a bit more complex because you have like a bus and you don't know how many people are on that bus without actually looking at the data from the transit agency. And then same thing for like the LRT. So we had to use something called GTFS. Uh, so it's, again, it sounds complicated, but basically it stands for General Transportation or General Transit Feed Specification, and it's just like a series of text files that have all this like spatial information, and they're really useful because they contain things like trip times, like bu bus routes, bus stops. And using that, we could, identify the relevant routes that we want to look at those key locations. We can identify like the stops where we want to see like how many people are on the bus after that stop. And we can also see that per direction. And then we can sort of pass that on, like me and the other undergraduate student, we would pass it on back to the grad students to actually like match all those stops to like the data and then make their calculation for mode share from there. But the real challenge was automating this process. So I'll explain screenlines and cordons. So basically, a screenline is the way that we sort of like it's a key area of analysis. So typically you would place it like right before or after an intersection. Like this picture's not that great, but it would like be a bit behind. And it'd be an important boundary. So over here, if anyone recognizes this, this is like the south end of like Uptown Waterloo. So essentially, this is a key place where we want to know like how many people are riding transit through this stretch. So it samples travel behavior, like that we hope is representative. And we put there wouldn't just be one screen line, there would be like dozens, right? And then cordons are similar, but the screen lines just form an enclosure. And it can just give you more granular data because you're accounting for ins and outs. So you can kind of see whether trips are like going in and staying inside, they're passing through, or if they're like mostly going out. Um, so basically, based off that, we came up with like a methodology of like how we're going to automate it. So we were using something called ArcGIS Pro. So it's like a software to do spatial analysis, like as I mentioned before, like sort of what GIS is. So it has like a mapping interface. You can bring in all these layers and you can like use these tools to like manipulate them. So you draw a screen line, and over there you can see in purple like that line across. It's like the same one that's over here on William Street. That's the screen line. And then we'd bring in like all the transit data. So you can see like some of the stops there. You can see the routes. And then we would use something called Model Builder. So Model Builder is like a feature inside ArcGIS Pro. And basically what it is like it's like a visual programming language. So you can do geoprocessing workflows. So it sounds complicated, but basically it's that picture over there. So instead of like manually using each tool to like do whatever you need to do, you could automate the process to where if you just change the input, which would be like the screen line, then it could replicate the same process without having to manually do the work again. Um, and so basically the process was like simple, at least the process we initially came up with. It was like select the intersecting routes, so the routes that intersect the screen line. Um, you would extract like any stops nearby just to like make the analysis smaller. And then you'd create a point at the screen line and route intersection, which is that dot in red. Um, so just there would be multiple, but that's just one example for like where that route crosses the screen line. And then we'd use like a spatial proximity tool to find the stop before. And before is in quotations here because it didn't really work. And we'll talk about that. And then we would output the stops of interest and then, give it off, and they would just get the load data from like the transit ridership numbers, and everything would be good. You get our transit mode share. But we ran into some challenges. Um, so again, like it's really simple in theory, but in practice a bit hard. Like if I told you all to identify which stop so this is, we drive on the right side of the road in Canada. So, this direction goes that way, and then the bus on this side goes this way, right? And if I told you guys all to find me like the stop right before the screen line, you would all be able to tell me like, oh, it's this one. But in terms of automation, it's not that simple because you need to actually have like the stop sequencing. So we need to know like which way the route goes and like what stop comes before the next one. And so we kind of forgot to consider that in our initial methodology. So really what upstream and downstream means is that imagine this is a river, so the river flows down this way. And then if you're here, this would be upstream, and anything there would be downstream. So really what we want is the upstream stop, because whatever the load is here on the bus, that load is going to cross the screen line. And when it crosses the screen line, say there's 20 passengers, that's the number we want to get, right? And so we had thought about the distance part, but we didn't really think about the stop sequencing. And one of the key challenges is that in the data, like in those spatial files that we got from the transit agency, directionality isn't necessarily explicit. So it's kind of there is like a direction for the route, but it's hard to kind of tell what direction the stops go in. It's not super easy to use the right attributes. but it is there. Um, so we tried to solve this by using something called shape point sequence. So to put it really simply, just like I drew this screen line here, someone drew these routes and they drew it in a certain order. And so the shape itself can be used by multiple routes and multiple like route branches. So the problem with trying to rely on the shape point sequence, so like that's like the order that the shape was drawn in, is that it might not match the stop order. So it's not reliable if you're automating because it could just give you wrong results. The other issue is that model builder, it's very visual and, it looks fine here. There's like only a few things, but in a few slides, you'll see it's like this massive, horrible thing. Um, so it's pretty unreliable. It really it couldn't handle like the exceptions and like the branching logic. And it was really overwhelmed by the iteration because again, we're doing this process. So even on that one small screen line, there's like 5 routes that intersect. So it's doing each of the 5 routes and then it's doing each direction on those routes. So you can imagine if you put like a bunch in, like it's just completely overwhelmed. So the output really just broke down and we realized like that's not really going to work. So we decided to revise the methodology. So this is like what the GTFS files look like. So again, there's a lot of files, and it was a matter of going in and finding which attributes could be useful to us to like fix the problems we were facing. So firstly, like as an alternative to model builder, we decided to use a Python script, and I'll talk about that more in the next slide. But basically, the new methodology, it was pretty similar. So you'd still draw the screen line, you'd still bring in like all the transit files, you'd still select the intersecting routes. But now we could determine stop sequence from this stop times file. So we hadn't previously looked at that uh, because again, like we don't really care about the time when the bus comes, but then we realized like this is actually valuable to us because it has that feature in it. And then we could associate each stop with a shape point sequence. So we had like the shape point sequence idea before where, the shape point can tell us, you know, if this, if the shape was drawn this way, like where like if we have a point right here and we associate it to the nearest shape point, then we can sort of tell like what comes before and what's after. But we didn't have that for the route. So now we have both, and that kind of allowed us to actually um, classify this like the stops around it as either being upstream or downstream. And then that's ultimately what we're looking for, right? We want to find the first stop that is upstream. So when I say selecting the max, that would be so you'd literally get like a stop number, maybe 22, and then after just 23. And so we'd be like, if 22 is classified upstream, then that's the one we want. And then for cordons, so where it's like an enclosed shape, it's pretty much the same. We just want to also know like if stops are inside or outside the cordon, just to have like more data. And then record those transition points. So anytime it switches from being inside to outside, then that's significant. So yeah, Python script. So I know this looks like probably gibberish to anyone who's like not in coding, and neither am I. Like I'm a planner. I don't know how to code. So this was like intimidating for me. Model Builder is like a lot more visual. So for me, I was like, I'd much rather do it, but it just wasn't working in Model Builder. Scripting is a lot more efficient because it can compare elements versus like Model Builder is like comparing entire data sets. That's really slow. So like running the script was a lot faster. It also just handles the logic more clearly. But the way Python was useful to us was really because it can support something called like spatial libraries. So one of them is called GeoPandas, and I can't really explain to you like how libraries work in Python because I don't understand it. But basically, this gives it capabilities very similar to GIS. So you can do analysis with spatial features. Um, and since we pretty much had like the methodology ironed out, like as I mentioned here, it was kind of easy to have AI help like create the actual code. And luckily the other student working with me like had a bit more coding experience, so he was able to like revise and make sure it wasn't making any mistakes or it wouldn't create any issues down the line. So the only real downside is that you can't easily draw like a screen line in Python. Like you could, but you'd have to know how to code well, and you'd have to know like the exact coordinates of like where your screen line is going to go. And like that's not how people draw screen lines. Like usually you'll just zoom into the mapping interface and like a software like GIS, and you would just like place down one point and place down the other, and then you would draw it. So you kind of have to still do that and then import it into Python which is an unfortunate downside, but it's not a big deal. So yeah, comparatively, there were two blocks of code. The first one installed like the libraries and like the plugins, and the second one did the actual analysis. And that was like maybe 150 lines of code compared to like this mess that would take like 8 minutes to run and it like keep failing. Um, so yeah, this was the model builder. And then we had like a third block of code to create visualization. So as I mentioned, JS has like a built-in like mapping like interface. So it's easy to see like to like kind of visually check the results, make sure it makes sense. Because again, like finding the stop before the screen line is super easy visually. But if you want to automate the process, then that's really where like it gets challenging. So to make up for that, we had to actually plot like the results in this sort of map, and then you can do like a quick eye check. So I mean, even here you can see like it got all the stops that are like before on this side, like going southbound, and then same thing going northbound. And then this one route that's like that stop right next to the screen line, it actually has like a loop. So that's also the stop before. And so we did that for a number of screen lines to check that it works well. And we checked the logic and everything was good. Um, so yeah, this is actually what it outputs. So this is like the screen line output. So this is actually what the grad students wanted. So it would give you the line. So you could see like line 5, and then that easy go is like the ID of the stop, the bus stop. And then you'd have the direction, and based off that information, you could get the exact bus load at any given time of the day. And then you would like add that up to be like the transit sort of like a number of people riding transit, and then you could calculate like the transit mode share based off that. And the cordon was pretty much the same. So the only additional attribute there is like the crossing type. So you can see if it's exiting or entering. So again, especially like in denser areas, like I showed in that picture was like downtown Kitchener, you can get like more granular data about like people's like travel behavior. Um, so yeah, I mean, ultimately, like the scope of the research was somewhat limited. So we did create this whole tool, but the tool only does like really one thing. So in an ideal world, if we had funding and we had more time, we could have integrated it with like actually reading the load data, like from Grand River Transit, but they didn't actually give that to us for one reason or another. So we couldn't really develop that. So there was still like a process where the grad students had to take this and then like I don't know how they were actually matching it to the load data, if it was being done manually or automatically. Um, but yeah, if we did that, then it would be as simple as drawing a screen line or cordon and then clicking run, and then it would give you all the transit ridership in key areas. Um, and ideally, like you could actually integrate it like with the rest of the data. So you could um, integrate it with like the other transportation mode data, and then it could actually be like a larger script that does even all the mode share calculations for that. And then that way, all you would really need to do is just like put in the data and then like validate it. Um, so yeah, I mean that's pretty much what we worked on. And so I'll open up for questions, inshallah.
My question is a bit preliminary. With the first slide that you showed with the survey of like the motor transportation, I guess in Waterloo KWC region.
Yeah.
How did you get like who are your like the people who filled in your what's the word demographic? Like, who did you target?
So this is done using like Transportation Tomorrow survey. So it's from like a regional transportation plan. So they target everyone. They try to get as many people to fill out this survey. Sure.
We build in data.
This data, so I mean, actually, technically, you could it is publicly accessible, but I don't know. Like a lot, like they'll get like factors based off like representation, so they want to make it accurate. So they'll use census data to like validate to like kind of account for response bias. But that is kind of the downside of doing it in a survey, like with a survey, and that's kind of the advantage of this analysis because it's actually like based off like real conditions. So the load data is real. It's actually people riding the bus. And then the cameras are actually like recording like live traffic and people crossing the intersections and so on.
Was there a reason to use GeoPandas and not like ArcPy?
Um, I think the main reason is that we felt like ArcGIS like couldn't really like support like the whole thing. So we're like we could use ArcPy, but we were like GeoPandas is kind of like simpler and like like I couldn't fully tell you also because I don't know the code well. So like I was just literally like, okay, like let me tell the whole process to AI and like see what it out.
I wonder if I would have allowed you to draw and like export.
Yes. No, like that's a good point. I guess like we were concerned it would still have like similar like processing issues to like model builder where it'd take too long to run as well. But that's a really good question. Any other questions? Go ahead.
You talked about the motor analysis for Screenlines and cordons.
Yeah.
Did you ever get a chance to look at some of the data for cordons? Because I imagine having like a closed loop is a pretty interesting situation.
Yeah, so no, I didn't actually get to see the data. And then like even in like my professional experience, like when I work on like bigger plans, we always use screen lines. So it's interesting that they were looking at cordons. I guess like there's specific interest in like downtown Kitchener because the travel behavior would be like quite different. And especially like obviously downtown Kitchener has a lot of offices. So I think mainly what they're hoping to see is like are a lot of people commuting in during the like a weekday and then out like in the evenings, for example. Does that answer your question?
Yes. Yeah.
Okay. I'll go in the back.
How did you pick this specific area?
Okay, I didn't pick it. It was the professor gave it as like examples. But there was like a number of cordons and screen lines. So there's like dozens. So these were just like test ones that we used. But ideally, the way we developed the tool is that it should work anywhere. Yeah. You had a question?
I'm wondering if you can use Google Maps to draw a street line for you, screen line for you.
Yeah, that's a good question. So you can't because in order for it to be like spatial, you can like analyze it spatially and to be read in like GIS or by the script, it has to be something called a shapefile. So that's like a specific file type that like you would need like some kind of a software or script to create.
But for example, for screen lines, they're only determined by two coordinates.
Yeah, for the screen line, I mean, it could be more like if it's not straight, like if there's like a kink in the street, like it could be more, but it's just like a line generally.
How did you like kind of validate your findings? Like, let's say you've come up with a mode share analysis.
Yeah.
How do you know that they're accurate or like even in the same ballpark?
I mean, you would still have an idea. So as I mentioned, like there is like the census data and there is data from previous years. So like including this, it's from 2016. So like obviously if like your auto driver went from like being close to 70% to like 30%, you're like, okay, like that's not right. So there is still ways to like to validate it. And like again, over like even 10 years, you wouldn't expect to see like a really massive difference if there wasn't like huge changes in infrastructure. Obviously, like the ION did come in. Bus service is probably better than it was in 2016. So if you saw transit was a bit higher, you'd be like, yeah, okay, that makes sense. But if it's like super high, you would, lift an eyebrow.
Data more recent to 2016?
Say that again, sorry.
So data more recent to 2016?
Yeah, so there's the census data. But as I mentioned, like the census data has a number of limitations, just because it's like focused on commuting. And so that was the whole point of making this so that we can have like 2025 data.
Walking brings insight in school bus, like the data would be changed from 2016 to even 2019.
Exactly.
Why did your professor choose 2016?
No. So this is an example I'm giving to like explain the data. But so no, this was being done for 2025 to be clear. I should have kind of made that more clear earlier. So often like the way mode share is typically done is they do it in big plans. So like this is from the region of Waterloo's transportation master plan. And then like those interim years, which can be like quite a few years, it could be like 10 years. Like there's no official data a lot of the time. So that's why region of Waterloo wants like to have like this recurring process and ideally automated. So it's like at a lesser cost for them to get more accurate data like every year, every few years.
I was going to mention that if census happens every 5 years, and the last census was in 2016, the last actual census, then you'd have a census in 2021, but that kind of isn't as maybe people don't think that's reflective of the actual conditions because it was in a COVID year. Especially can't match that, even though the census is accurate, you can't match that with a transportation to more surface.
For sure.
Yes, things were disrupted. People didn't even need to go to the office anymore. So most commutes have been canceled.
Yes, 100%. And that's like another issue with like having data from 2021. So again, that was like the whole reason of why they wanted to like have it like more up to date and in the future do it ideally more often too. Very good point. Any more? Mashallah, you guys had a lot of questions. I'm impressed.